I'd like to thank you to the conference organization for the opportunity to be here today presenting the present study. It's a great honor to me to be here, and I'd like to thank for everyone to watch this presentation. First of all, I'd like to declare a conflict of interest regarding the ownership of the patent of the object of the present study. Since the 70s, the video surgery experimented a rapid grow-up, and this phenomenon is due to the creation of better quality equipment, especially video equipment, that allows the surgeons to do more complex procedures and improve the work quality, although some problems. So, one of the most important problems that we will solve is the optics blur during surgical intervention, causing laparoscopic blindness, as you can see in the short video. When used on the video surgery touch, the blood inside the human cavity, it becomes totally blurred, and the surgeon cannot see what During the last decade, some devices were created to solve this problem. And the main purpose of all of these devices is to clean the optics when it becomes blurry. Some of them have observable surface that removes the residue when surgeons touch them with the optics. There are devices that wash the optics, and some of them heat optics to avoid the formation during the surgery. But none of them can prevent the laparoscopic blindness. For this reason, the present speaker decided to look at the nature and see how the evolution solved this problem on natural optics that are the eyes of the animals. The nature and the million of years of evolution gave us a perfect out-cleaning device that consists of lacrimal ducts that release tears in eyes to wash any air suspended particle or foreign bodies that contact our eyes surface. Inspired in this natural solution, I decided to put a lacrimal duct on surgical optics that originated the concept of the LacrimaSurg. This video, this short animation show us how the LacrimaSurg works. It's so simple to understand and so intuitive. Here we can see inside of the pleural cavity. During the surgery, when the optics touch the fluid or the body inside of the human body, it becomes totally blurred. And you can see the optics touch the blood and it becomes clean. And the laparoscopic blindness does not happen. And to test the solution and to prove that it really works, the authors decided first of all do a vivo study and to evaluate what was the behavior of the device in some situations that the optics become active. This study consisted in immerse the surgical optics of 0 13 angle objective in 3 different materials that potentially mask the optics. Each optics were immersed into material for different times of exposure, and each immersion were considered an experiment and repeated 10 times, giving us a total of 420 experiments. After each experiment, the optics was pointed to a right surface with black letters printed on it, and successful experiment gave the investigator the possibility to see the lacquer perfectly by the video. When optic blindness, when laparoscopic blindness occurred with the need of stop the experiment to clean the optics, the investigator considered the fail of experiment. The great majority of experiments failed occurred when the authors used blood plus fat to immerse the optics, as you can see in the green bars. But despite of the fail, the optics was capable to prevent laparoscopic blindness in 97% of all experiments. But in ex vivo environment, the optics show that it's totally effective. The device was totally effective to prevent the laparoscopic blindness. But to use it in surgery is necessary to prove that it works inside the human body and to prove that it's totally safe to use in real surgical environment. For this reason, we decided to do the present study, the pilot study using real surgical conditions. The study was submitted to the University Ethics Committee and was approved. And only surgeries with a low potential of conversion to open surgery were included in this study for obvious reasons. Investigators operated the patient and recorded the procedures on digital media for further analysis. And here is the photo of the prototype that of the device that the investigators used to perform the study. The prototype was constructed using sterile surgical material. In this case, a gastric tube attached to the optics using a sterile surgical tape. The investigator registered the patient's data, including the age, gender, body mass index, to verify if the body composition of the patient has any kind of influence in laparoscopic blindness, and the comorbidity Charlson index that revealed to us the severity of the patient's malady. The environmental data was recorded too, including the temperature of the patient's body and the room's temperature, and the data regarding the procedure. Each procedure were recorded: the type of surgery, the surgical time, intraoperative complications, and all of this data we recorded. Prior to each procedure, the investigators collected blood samples from patients prior and after each procedure. And this blood sample was used to calculate the ionic titration to evaluate if the devices used could cause any kind of an electrolytic disbalancing on the participants. Movies were analyzed to evaluate the following events. Data were recorded and analyzed using the following software. And all variables exhibited parametric distribution. And the author considered that a significant different values were that values with a two-tailed p inferior to 0.05. The investigators performed 13 surgical procedures using the device with a 30-degree optics. The participant mean age was 49 years. 13 were male, 70 female, and the CCI, that is the child comorbid index, was 2. And the body mass index was 24. Here we can see the surgical indication, the procedure indication. The participant elected the investigators elected only short duration surgery with a low risk of conversion to open surgery. The mean crystalloid flow was 230 milliliters, and the mean flux of crystalloid was 134 drops per minute. Here you can see the result. In half of procedure, the optics did not become dirty. When it becomes massive, in great majority of the cases, the device was capable to clean itself without the need of surgical interruption. In only 3% of procedures, the laparoscopic blindness occurred, leading to surgical interruption. Here we can see a video of an impediment surgery. You can repair that when surgeons touch the purulent material inside of pleural cavity, the optics did not become massive. The laparoscopic blindness do not occur. In this other video, we can see that the optics become massive, but the administration of jets of crystalloid using the device was totally capable to clean itself. And the surgery do not need to be stopped to clean the optics. Analyzing the group that the optics become dirty, the author looked for variables that could potentially contribute to increase the chances of laparoscopic blindness. To evaluate the correlation between the laparoscopic blindness and continuous variables, the author performed a simple linear correlation. And in this table, we can see that the result of this correlation, and there was no significant correlation between the variables. The Fisher exactly test did not reveal any correlation between the type of surgery and the number of times that laparoscopic blindness occurred. and there was no significant difference between the pre and post-operative blood ionic titration, and this suggests that the device is safe to use in real conditions. Complications occurred, but they were related to underlying participant maladies. As you can see, that the patients that had complications had a high char comorbidity index that revealed to us that these participants have so bad maladies, and were not related to device use, all these complications. No cases of congestion or anasarca or any kind of edema were reported, and this fact reinforced that the device is safe. All devices created until this moment are capable to clean up, but no of them can have the capacity of dirt prevention. LacrimaSurg gave us the possibility to operate 97% of cases without need of interruptions to clean the optics. No variables have significant risk of laparoscopic blindness, and no complications related to the use of the device were registered. All the complications were related to the participant's underlying disease. In conclusion, LacrimaSurg is efficient and safe and is a potential solution to laparoscopic blindness. To improve the device and reduce the lack of 3% of cases that surgery must be interrupted to laparoscopic blindness, I've did some modification on the original device design. And the other modification that I'm working at this moment is to create an automatic crystalloid flux regulation using the Arduino technology. But I'm a medical doctor. I'm a surgeon. I'm not. I do not have experience with the Arduino. For this reason, I asked to my 9-year-old son to help me with the Arduino programming because he do it so well. I'd like to thank you for everyone to watch my presentation. And I'd like to thank the organization of this conference for this opportunity. Thank you.